Our next speaker is Hanne Sagen from the Nansen Environmental and Remote Sensing Center in Bergen. And her title will go up in a minute after the initial pictures.
I am hidden it. So, first a couple of words to Walter and also to the group at Scripps. I thank very much for inviting me to come here for this great occasion. And I also want to thank Walter for being who he is and being so inclusive also for us who come from the other side of the Atlantic. We have had the pleasure to have Mary and Walter visiting several times. The last time in 2014, just before this Normandy event. And you can see some faces that you know here, but also on the upper right hand, you see Walter with the young people that I'm working with at the Nansen Center. And at the lower picture, you see my son and one of my colleagues with Walter at the Fløyen in Bergen. That is a must to visit when you visit Bergen. And then here you see Mary and Walter. They are going back home, and they had a lot of luggage. So, so we had to bring this, what do you call it? Trailer. Yeah. But we managed, didn't we? And this is my favorite picture of my daughter and Walter. My daughter is showing the high school book in mathematics. This is 3 years ago, and now she is a student in oceanography and meteorology. So I think you had a big influence here. And here is the result of 10 years collaboration with Scripps and with us in Bergen. We have done a lot of work in the Fram Strait together, and I'm very happy that we have had the possibility to work together. And that has been due to funding from the EU and also from some private sponsors, and also from the Norwegian Research Council and from Office of Naval Research through many years. So I'm very grateful for that. And you can see that there is a number of people with me at the Nansen Center working on acoustic thermometry and passive acoustics. And we work with Peter's group here at Scripps. And we hope that we can continue with that in the future. So my title is Acoustics, the Key to Observe the Ocean Under the Arctic Sea Ice. I will give a little bit of motivation, although the two Peters have already said a lot why we do it. And I will also talk a little bit about the gap in the Arctic observing system, how we can use the multi-purpose acoustic networks, and what we have achieved so far in Damocles, Akbar, and Under Ice projects, and how we transfer this into the new project in Taros, and a bit about the German initiative, the Mosaic program, which is to let the polar stand drift across the Arctic Ocean for a year, and then a bit of an outlook how we can benefit from this doing acoustics. So, as Peter said, the Arctic is extraordinary. It's warming much more than the other regions, and therefore a key for observing the climate change. And this is also a plot that Peter Wadham showed. And you can see that the observations are showing that the sea ice extent is decreasing much more than the models can predict. And that is most likely, or it is, because the climate models are not including all the processes that we observe in the Arctic. They are not capable to do that. And they have to be kind of checked up so that we know how bad is it and what should we do to correct for it. So that means that we need to understand the key processes in the Arctic, and we need more observations. So one of the key things in the Arctic is this blue cold water on the top here, which is so far isolating more or less the ice from the warmer water below. But as Peter says, when the ice is getting thinner and more fragile, it opens up for more interaction with the atmosphere, and you start processes that we have not had in the Arctic before, and therefore you might lose this isolating layer, and we can get the increased thinning and melting of the sea ice. So our key questions is how much heat and fresh water goes in and out of the Arctic through the Framstrait. That is what we have been working with for quite a long time, to try to combine the acoustic with the ocean models to do some better estimates of this transport. And then how much heat is stored already in the Arctic basin. I mean, so far we have tried to close the boundaries to learn about how much heat is going in there and how much goes out. But now maybe we should go in there and measure again the heat content and compare to what Peter Michalewski did in 94 and 99. And you can also on this map see some dots, and that is the buoys that is used to measure ice and also some of the ocean parameters. And it's not so many, and you can in particular see that it's quite empty in the eastern part of the Arctic. So we need more observations here, but at the same time, as the ice is getting more fragile, it's more difficult to deploy long-lasting ice stations in the Arctic. And then the last question that we have put up is how will the freshwater content / upper ocean stratification evolve in the coming years? So we need more observations, and one of the most advanced monitoring system in the ocean is the ARGO program. But as you see, there is no one up in the Arctic because it can't come up and transmit the data. That is one thing. And even if it could, you don't know exactly where it has been because it has been under the ice for quite a long time. And if you can't position your data, it's not so useful. So what we propose to do is that we have multi-purpose acoustic networks in the integrated Arctic observing system, and use of gliders and floats in ice-covered regions. They really will depend on this implementation. And if you use a fixed underwater acoustic network, you will have the underwater GPS for all users, not only the ones who are planning an advanced experiment. You can also use this to monitor the acoustic environment so that you can get some baseline data before you get changes in the traffic in the Arctic, for example. And you can do thermometry, which is really what I would like to do. And then you have the drifting acoustic networks, which are cheaper and more accurate as long as the float or the glider is inside the range. But then you invest quite a lot of things just to go out for that mission. So what we think and what we proposed in the paper 2 years ago, which Michalewski was leading, was a combination of fixed moorings and then drifting GPS systems. And you can see that I marked out the Fram Strait. That is where we have been working for quite a long time, and I will come soon back to that. This is a more recent plot. It's my PhD student who have used the OASIS model to look at the propagation at 900 hertz, and you can see how nicely the sound is divided into portion that goes into the sound speed channel near the surface, and then the deeper going rays. And that means that we can hope for information, as also Peter said, separated. You can look at the deeper water masses separated from the more shallow water portion of the ocean. And the lower plot shows what happens if you put in sea surface roughness. That we have to be very careful when we choose the frequencies that we are going to use in accordance to what the ranges we want to reach. So back to the multi-purpose systems. We have been implementing in the Fram Strait over the last 10 years, 3 experiments. And also Peter have used the same system in the Canapé. So now we have experience from 2 regions. So we use the same system, both of us. It's a web sweeper source integrated with the D-Star controller. Of course, I have just 2 sources, and Peter have a lot of them. And he have a lot of hydrophone modules. But I have 2 sources, and I have 50 hydrophones now. So I can do a little bit. And this is the receiver, the star receiver, and the hydrophone module, which is also giving me temperature. So this was the first experiment, and then we did not have these nice hydrophone modules. We had cables, and I only had 4 hydrophones on each of the stars, which is on 2 different levels here. So I had the 700-meter long array and 1 source here in A. And from this, we did we have inverted this, and Brian Dushore have developed a technique where he can invert. So first we process, and then we get the dot plots, which is then going into the inversion. And Brian produced these blue line of temperature, and the green line is Emanuel Scarzoulis, who have used another method. So it seems fairly robust. And we also compare with the CTD mean temperature from CTDs in the beginning of the experiment and at the end of the experiment. So it fits fairly well. Then 2 years later, we were out again, and then we expanded. So we had 3 sources and a receiver array in the middle, and then also the RV mooring array across the strait, which has been monitoring the cross-section since 1996, I think. And we have used this for acoustic thermometry, and EOPAN used this for geopositioning of a glider. And also we have analyzed it as passive acoustics. And this is the dot plots from this section is here, and this section is the middle one, and this section is this one. And you can see here, for example, it's a lot of arrivals coming in, and this corresponds to the waterborne part of the signal, and then you have reflections from the seafloor. And you see here, this one goes through warm water and goes into cold water, and also the bathymetry leads to this result that we have only a few or a thinner arrival pattern and not as clear reflection pattern. And then here you see that it is this waterborne part and then the reflections. This is after Matt Datchew have done estimator correlator, and you can see that he cleans up the signal quite a lot, and we are able to trace the arrivals. But now it's not anymore clean ray tracing, so he had to go back and look into the sensitivity kernel, which you saw yesterday. This is Brian, who have used the arrival times to invert, and he have produced these time series. And you can see that he is well above the World Ocean Atlas climatology. In particular for this B to D, that is the one where water is coming out from the Arctic. This is in the West Spitsbergen current, and you see that it's closer. But you can also see these large variability. And then if you look at this one, you also see that we are above the climatology quite a lot. It's almost a degree. And this is the passive acoustic data that we have. We have looked into the natural sound, removing all these events with mooring motion, because that caused a lot of strumming. And also we have looked into the seismic, and we have observed that almost through the whole year we have seismics in the Fram Strait. This is the latest experiment that started in 2014 to 2016. We are currently analyzing the data, processing the data. And here is an example. So you can see all the way in here, you have the seismic signal. And here you can see the source. And here, and here, and here. So we just started to produce the dot plots, and Espen didn't want to show you that because it didn't look so nice yet. So maybe next time. Here he have detected the signal by match filtering. So the status is that we have done the 3 experiments. We have a production line established for range depth average ocean temperatures. We have also used the data to look into how good the models are. We have considered HICOM and ECHO. Matthew have done the estimator correlator and is currently working on the sensitivity kernel. And we are also working on the assimilation, and that is a tough task. So we are working with Bruce and also with Patrick Heimberg on this, and we hope to make progress using the results that you saw from what Bruce have done in the Philippine Sea. But we also see that we have a lot of experiments now, and it calls for data management and also standard procedures and data products, and that will be followed up in the INTAROS project, Integrated Arctic Observing System project, which is coordinated by Stein Sandven. And the objective is to develop an efficient integrated Arctic observing system by extending, improving, and unifying existing and evolving systems in the different regions in the Arctic. And that involves also multi-purpose acoustics networks. And it's part of a cluster of project. So you have a coordination unit and 2 modeling projects. And there is an Arctic permafrost project. And then you have INTAROS, and we are mainly looking into the observing systems, but we have also applications which includes climate modeling. So the focus areas is pan-Arctic, but there is a particular focus on the Central Arctic, because it's the main gap. I mean, the ocean under the Arctic sea ice is the least observed in the Arctic. And in this case, we will work together with Mosaic. Mosaic is Avi, who is going to let the polar stand freeze in for a year in the Arctic and drift as long as it can. And it will be a multidisciplinary drifting observatory for studying of the Arctic climate. And that means that they are going to put out a lot of instrumentation next to polar stand. And there will be, I think, 5 nodes, and it will be equipped with all kinds of sensors, both in the ocean, in the ice, and up in the atmosphere. And you can go in and have a look here. They have a lot of material with science plans and everything. So our plan is to use the hovercraft that we have in Bergen. That one is already equipped with some oceanographic instrumentation, but we can also house different kind of instruments in addition. And the plan is to hang a source under the ice next to the hovercraft. And Yngve Kristoffersen, he have been in the Arctic before. He drifted 9 months with this boat up in the Arctic. And he feel very good now when he can out again, and also that he can stay close to polar stand. This is KV Svalbard, so we tested how to bring the hovercraft with that ship in 2013. And this is the source which is under evaluation. We don't know yet which source we will use, but this is a geospectrum source, which is one of the candidates. Then to match this or to get funding, I'm going to address the Research Council of Norway with a proposal, and we call it the Coordinated Arctic Acoustic Experiment. I got the thermometry here. It's an acoustic thermometry experiment. And we aim to cover the Central Arctic with acoustic thermometry in order to estimate its current heat content and decadal trends, also to identify uncertainties in heat content, estimates from the global climate models, and create some baseline knowledge about the acoustic environment. So we aim for US funding and Norwegian funding at this point. And US coordinator will be Matthew Detchu here at Scripps, and I will be the one representing Norway. So I will propose to the Norwegian and Matt to the US side. So the principle is quite nice, I think. So we hang the source under the polar stern, and it will transmit as it drifts. So it's similar to moving ship tomography. It's just that we do not control the ship. And you will have a lot of these transects, meaning that you get the insonification of all this area, but it will be time and space mixed. And therefore we also plan to have acoustic transceivers here, so that you have a fixed line. So you have the moving ship and a fixed line thermometry. And we plan to have the sweeper sources in the yellow points here. We do not plan to have big investment in new sources for the moorings. And the three moorings here will be Norwegian ones. This is just a drawing, so Matt have to decide how many he wants to have, but I indicate the two here. And this is what I had to present for you. And I want to say thank you and congratulations to Walter from the Nansen Center in Bergen. And you can see here, this is the people at my institute. We are quite a few nations, and we speak mostly English, although it doesn't sound like that when I'm talking. So sorry about that. And then, I don't know, do I have time for this small film? So this is a film that we made for the Intaros project because we wanted to promote it outside to make it more eatable for people who are not in science all the time. So, and there is some Norwegian music. Some people, they like it. Others find it a little bit stressing, and I'm sorry about that. So, please. Yeah, we hope that. The problem is that the Russians said that they would fund those building the H2020. There was a kind of a indication of that. But all the funding went to the modeling projects, not the observations. Maybe there is a reason. I don't know. What do you think, Peter? No, so the intention is And what I hope for is to get the Russians involved, because if you saw the shadow area, for example, we missed the inner part of the basin.
Thank you, Hanne. We're running about 15 minutes.